Hi, my name is Logan Thomas, and this is Team 1's presentation for Phase 1 of the Big 3 project. On my team is Jake, Audrey, Jacob, Tyler, myself, and Jacob.
For the first design phase, Logan Thomas and Jacob Niles were in charge of the structures part of the design. Audrey Cruz and Jacob Wilmoth were in charge of the propulsion and power, and Jake Garrett and Tyler Niskanen were in charge of stability and control. Additionally, Tyler Niskanen was the first design phase team leader. The design aspects that our team was trying to meet was to be on station in about 3.5 hours. We also wanted to reach a loiter altitude of 55,000 feet, and finally to house a payload package that would give us a specified field of regard.
In developing our configuration, we considered three major design concepts. The first was a blended wing design. We were hoping that the extreme taper ratio near the root would allow us to place our side view sensors there and get a full FOR there. We also thought that the smooth transition between the fuselage and the wing would decrease our parasitic drag. However, the small fuselage that a wing like that could support would not be able to contain enough fuel for the long endurance mission. The second concept was somewhere between a canard and a tandem wing, which was believed to create more lift as well as provide a greater CG location tolerance. Unfortunately, the wing interferes with the front wing interferes with the flow to the main wing, which increases our interference drag. Additionally, a canard decreases the possible angles of attack the aircraft can sustain without stall. Our third idea was a tanker concept that we estimated would have a large enough capacity to support both the necessary fuel and payload to complete the mission. It also provided us with a sufficient field of regard to support the requested sensors. The concept is heavy, however, and we knew it would take some work to achieve the requested altitude. When we compared the three design concepts, it became apparent that our best option was to adapt the tanker design. Through several iterations, we arrived at our current parameters. We have a large wing with a 160-foot span and an aspect ratio of 13.5. Our fuselage is 80 feet long. Throughout the mission, our aircraft has an average cruise altitude of 35,000 feet, climbing to a loiter altitude of 55,000 feet. Our cruise Mach is just under 0.5, and our loiter Mach is around 0.7.
For stability and control, we used the CG Excel spreadsheet to calculate our static margin, which we calculated to be positive with our loaded CG at 41.73 feet from the nose and our aerodynamic center at 41.75 feet from the nose. We're going to have traditional control surfaces for large aircraft, ailerons, elevators, rudders, etc. We have a rough calculation for our horizontal and vertical tail areas at 144 and 102 feet squared respectively. Our wing area is right now at 1896 feet squared. So some of the possible problems we think we might run into with the finalization of our design is the aft placement of the wing. It could cause yaw instability. So to counteract that, we're looking into using a large vertical stabilizer. We've moved our wing as far forward as we can while still maintaining a stable aircraft. Our unloaded static margin is currently very slightly negative. We think we can fix that with composite structures in the vertical and horizontal stabilizers.
Possible issues that we thought of for this design structure are the high wingspan that might cause bending moments during high loading. But as you can see from our diagram, we have plenty of room for wing box structure between the fuel tank and the rest of the wing. We decided to go with a traditional blend of composite and aluminum for the structure, so it's both lightweight, strong, and cost effective. The weight breakdown is as follows: 150,000 pound gross weight with a empty structure weight with engines included at 61,000 pounds. The weight of the fuel is 76,000 pounds by itself, and that's all the gold that you see. Most of it's located in the wing, so that way it doesn't affect the CG very much during flight.
The propulsions team has chosen to go with a high bypass turbofan engine. This maximizes overall efficiency for long endurance while producing enough thrust to sustain takeoff. To save on structure weight, the team decided to go without a mixed exhaust. It was decided to go with two engines to fulfill thrust requirements, They will be placed under the wings and close to the fuselage to limit the required support structure. 2 engines will also allow for redundancy in case of an engine failure. The calculated uninstalled minimum thrust for takeoff was about 10,800 pound force. The max allowable specific fuel consumption was calculated to be about 0.6 pound mass per hour per pound force. The lift-to-drag coefficient ratio was calculated to be about 18, and the total endurance was calculated to be 23.6 hours, and the total capable range was calculated to be about 9,900 nautical miles.
In conclusion, we have optimized our aircraft for our payload mission requirements. Our aircraft now exceeds an endurance of 23 hours, allowing for loiter time and cruise to and on station. It allows for the maximum sensor payload capabilities for a wide range of military and civilian uses as well, extending far beyond a range of 1,000 nautical miles. The aircraft is now a stable design, which we calculated based on spreadsheet CG calculations provided in the backup data. Moving forward, we would like to optimize the sizing of the vertical and horizontal tails, as well as create an accurate internal structure, including spars, wing boxes, and frame locations. We would also want to look at the material selections for specific aircraft parts, including the wings and the fuselage, where we would place our composite structures or aluminum structures, and if needed, titanium. We would also need to look at manufacturing methods, including composite layups and researching how we would lay up designs for a fuselage structure or wing structure wherever we use that composite material. We would also want to optimize our design calculations for the vertical and horizontal tail sizing in the next phase and update the CG calculations based on that. We would also need to look towards crew conditions and the living compartments since our aircraft is operating at a long endurance.
Thank you for watching our presentation, and we look forward to your feedback for Phase 1. Now, back to whatever is behind me.